Good evening. I'm Karen Taylor, Program Director of the General Society of Mechanics and Tradesmen, and I'm delighted to welcome you online tonight to the talk, which is part of the Labour, Literature and Landmark Lecture Series. I would like to express our thanks to Archtober and to the New York Landmarks Conservancy for the promotional support of this lecture. And I'd also like to thank Connie Mugno at Mugno Consulting for her assistance with setting up this program tonight, and Angelo Vigorito for providing behind-the-scenes support for tonight's talk. For those of you who may be less familiar with the General Society, a brief introduction. The General Society of Mechanics and Tradesmen of the City of New York was founded in 1785, 236 years ago, by 22 artisans. Today, the General Society continues the tradition of trying to serve and improve the quality of life of the people of the City of New York. And we do this through our different educational and cultural programs. These include our tuition-free Mechanics Institute, our John M. Mossman Locke Museum, our General Society Library, which celebrated 200 years recently, and finally, our lecture series, which is also nearly 200 years old, and of course, of which tonight's lecture is part of. At the conclusion of tonight's talk, there'll be a short 10 to 15 minute Q&A, but please feel free to submit typed questions throughout the lecture through the Q&A section. And of course, at the conclusion of the talk, please submit questions then. And we do ask that you use the Q&A section rather than raise your hand. Tonight, I'm delighted to be able to introduce to you Helen Thomas-Haney. I was fortunate enough to have a preview of Helen's lecture on Friday and was so impressed by Helen's vast knowledge of every aspect of terracotta and feel we are so fortunate to benefit from her expertise this evening. Helen M. Thomas-Haney is a principal at Jablonski Building Conservation with 19 years experience as an architectural conservator. Her expertise in developing carefully designed testing programs provide clients with a better understanding of what is possible in restoration and conservation. Helen's special interests include metals, masonry, and masonry testing, modern materials, and implementing conservation treatments. She is a professional associate of the American Institute for Conservation, a recognized professional with the Association for Preservation Technology, and is a former board member of the Northeast chapter of Association for the Preservation of Technology. Helen, such a warm welcome. Thank you so much for presenting tonight. Thank you.
Well, thank you. Good evening. As Karen said, I am Helen Thomas-Haney, a principal at Jablonski Building Conservation. Let me start sharing my screen here. So today I will be presenting to you on the repair and restoration of architectural terracotta. This presentation will include some background information, but the main focus will be on the restoration process, testing, and treatments. This will be a bit of a crash course in terracotta restoration, so please ask me questions at the end of this presentation if you need more information. So what is architectural terracotta? The manufacture of architectural terracotta in the United States began in the mid-1840s, but it wasn't until 1949, almost 100 years later, that the United States National Bureau of Standards officially defined terracotta as plain or ornamented, modeled or molded, hard-burned building units, larger in size than a brick, consisting of mixtures of plastic clay, fusible materials, and grog, having a glazed or unglazed ceramic finish. Terracotta was initially used for discrete elements like cornices and facade ornamentation, such as window surrounds and trim. The lack of material data, limited usage, and early failures resulted in a professional reluctance to use the material. However, advances in manufacturing, clay production, and the need for fireproof building materials made terracotta more popular. Eventually, the terracotta industry flourished in the late 19th and early 20th centuries as a less expensive alternative to carved stone. The basic fabrication process has remained the same for the past 180 years. Clay is shaped into the required form, dried, then glazed and fired. The 5 common methods of fabrication include hand-pressed, ram-pressed, extruded, slip-cast, and hand-sculpted. Hand pressing is the traditional method where clay is pressed into plaster molds of the desired shape. Intermediate walls, or called webs, are incorporated to strengthen the unit and limit deformation during drying. Ram pressing is typically used for flatter pieces like roofing tiles or small open units. It consists of mechanically pressing clay between interlocking steel plates under high pressure. Extruded pieces are created by mechanically pushing clay through a steel die, creating walls and webs with open ends on either side. For slip casting, a chemical deflocculant is added to the clay to allow the clay to flow, and it is poured into an interlocking mold. Sculpting is the least common method used to create one-of-a-kind large units. Installation methods for terracotta evolved along with the construction industry. As previously mentioned, terracotta was first used as a decorative masonry component, integrated into load-bearing walls. Units were filled with brick and mortar and built into the wall construction. As construction methods changed, terracotta was used more as a cladding material. Ferrous fasteners and attachments were used to hang the hollow or unfilled terracotta cladding to the building structure. Most historic terracotta buildings will have a combination of units partially filled with brick and mortar and open with ferrous anchors. No one case of terracotta deterioration is ever identical to another due to variations with the material, manufacturing processes, installation, and weathering conditions. However, there are some common causes of failure or types of failure. As with all things building related, material failure can be attributed to water-related problems, faulty original craftsmanship, stress, damage caused by later alterations and additions, or inappropriate repairs. These means of deterioration can cause glaze cracking, glaze spalls, clay body spalls, missing units, and deteriorated metal anchoring. The deteriorated metal anchoring, in turn, can result in terracotta cracking, spalls, displacement, and losses of entire units. But before you go making any repairs or replacements, any proper terracotta restoration project must begin with a survey of the facade and the material. Ideally, this survey must be performed up close and hands-on, as many conditions can go unnoticed if surveyed from the ground. Material failure of architectural terracotta is complex. There are both surface and subsurface conditions to be assessed. While surface conditions like spalls and cracks are easy to identify, the assessment of subsurface conditions require probes. Probes allow you to determine the condition of the backup masonry, the steel anchors and framing, and the internal webbing. Understanding the conditions and failures of the entire system allows you to develop better repair solutions. So, in addition to evaluating the major causes of distress, understanding the properties of the specific terracotta on your building is crucial for designing these repairs. The following list of tests on the screen here is not exhaustive, but it represents the most common tests that are performed to characterize terracotta and its deterioration. As you will notice, several tests are based on ASTM standards. ASTM tests are designed to evaluate new construction, but they can be adapted for historic construction, including reducing the sample number requirements, which may be difficult to achieve when extracting material from a historic building, and also the test results must be interpreted differently to account for older material that's been in service. But these test methods provide sound testing methodologies that yield useful information. So the first test I'll discuss this evening is freeze-thaw resistance. It can be evaluated a number of ways. Per ASTM C67, terracotta blocks are cut into 4-inch specimens, dried in an oven, weighed, and examined. The specimens are then completely soaked in water for 4 hours, after which they are placed in a tray with a 1/2 inch of water. The tray and the specimens and the water are then placed in a freezer for 20 hours. After the 20-hour freeze, the tray is removed and completely submerged in water to thaw for 4 hours. The specimens are subjected to 1 cycle a day for a 5-day work week. And this procedure is repeated until 50 cycles are completed. Now, if you've been following along and doing your math, you'll realize that this test will take 10 weeks to complete. And I've never had the opportunity to work on a project that had enough time to wait for 2.5 months to get testing results. And so that's where ASTM C66, did I say enough sixes? ASTM C666 comes in. While designed to test concrete, we often use test procedure B in this standard for its accelerated cycle times. Freezing takes 4 hours while thawing takes 1 hour. And that way, depending on the length of the day, one can get 2 to 3 cycles completed in a day, and the whole test can be completed in 3 to 4 weeks. Freeze-thaw results are reported as the number of cycles a sample can withstand before failure or deterioration is noted. A sample is said to have failed if it develops a crack, breaks, or appears to have lost more than 3% of its original weight. Once failed, the specimen is removed from the testing process. A question I'm often asked is, does freeze-thaw testing relate to any real-world conditions? And the answer is no. This test is designed to drive the samples to failure, and they are therefore subjected to extreme conditions. It's simply a durability test and not meant to be a straight correlation to real-world situations. However, it does provide valid comparative data to estimate a sample strength, as we'll see in the next case. So working with the architecture firm Goody Clancy, JBC was asked to test the terracotta on the Brooklyn Post Office to help explain why some of the terracotta, or to help explain some of the conditions that were observed with the terracotta during the survey. The drawings on the screen show the extent of the terracotta on the building, shaded in yellow. The dark gray areas are the original 1892 building constructed of granite. A terracotta and granite addition was constructed in 1933. And between 1990 and 1992, an extensive exterior restoration project was undertaken, which resulted in the replacement of significant amounts of terracotta. So the building contained a combination of 1933 and 1992 terracotta. So the facade survey found significant deterioration of the terracotta ashlar and decorative units, as you can see in these photographs. So JBC tested the freeze-thaw resistance of samples of original 1933 and 1992 replacement terracotta to compare their physical and mechanical properties. All of the 1933 terracotta samples from the east facade and one from the north facade failed prior to reaching 50 cycles. However, all of the 1992 terracotta samples passed. Ultimately, the results of the freeze-thaw test determined that the 1933 terracotta was weaker than the 1992 terracotta. Though there's no way to test the original strength of the 1933 terracotta, it can be inferred that the original material was either potentially weaker than the modern terracotta at the time of its manufacture, or it weakened over time with exposure. Regardless, the results of this conditions assessment and the probes and the testing resulted in the replacement of over 15,000 terracotta units. Excuse me. One of the most common forms of terracotta deterioration is failure or loss of the glaze. This failure is caused by pressures that have built up below the surface of the glaze, which causes it to pop off. Sometimes the glaze is not well adhered to the clay body due to flaws in manufacturing. And I'll discuss two methods for determining how well the glaze is adhered to the clay body. For the first method, JBC was called in to examine some terracotta copings whose glaze was coming off in sheets, as you can see in the photos here. Let me make my pointer a neat laser. Pew, pew. Sorry, that's my laser noise. So these were newly manufactured pieces, and so the age of the terracotta was not a factor. So we employed a rather simple test that was specified by the now defunct Architectural Terracotta Institute in their AIA file number 9, Public Works Specifications for Ceramic Veneer in 1961. Essentially, a metal bar with a 1 square inch bearing surface is epoxied to the terracotta glaze. Once the adhesive sets, the bar is knocked off. If clay body is attached to the glaze when the terracotta falls, then the glaze is well adhered. If only the glaze comes off, then there's a glaze adhesion issue. Tests showed that there was no problem with the glaze adhesion of these units. It was ultimately determined that soaking the units prior to installation and fully sealing the joints with caulk trapped water in the units, which caused the glaze to spall as the water froze. A second means of testing glaze adhesion uses ASTM D4541. While designed to test coatings, the application concept is the same. Here, metal dollies are epoxied to the glazed surfaces. The adhesion tester contains a claw at the bottom, which grasps the dolly. The tester is set to 0, and then the hand wheel is slowly and evenly tightened to pull the dolly from the terracotta. The tension is increased until failure occurs. In the example shown on the lower right image, the dolly on the left has a well-adhered glaze as the yellow clay body was removed with the glaze. However, the dolly on the right has poorly adhered glaze, where there was a clean separation between the clay body and the white underglaze. Unlike the bar test, this method is quantitative as well as qualitative. The force at which the surface failed can be measured by the tester. Microscopy is an invaluable tool of any material investigation. As a survey is used to identify conditions on a macroscopic level, microscopy is a survey on a microscopic level. It can not only magnify small objects, it can examine a subject's interaction with light, which can provide information about the structure and characteristics of the sample. Simple examination of cross-sections under reflected light can reveal important information. The presence and thicknesses of underglazes and glaze layers, and the surface texture of the clay body are detectable. The micrographs on the screen are from terracotta units on the same building. As you can see, they are not all identical. Differences in clay body, glaze color and thickness, and color and thickness of the underglazes are apparent. Each of these differences could have an effect on the way the terracotta weathers. Polarized light microscopy, or PLM, is another important investigative technique. In PLM, a special microscope is equipped with a polarizing light filter so that light waves travel in one specific direction. Extremely thin wafers of the sample material, approximately 0.03 millimeters thick, are mounted on a glass slide. The samples are so thin that light can pass through them. This makes it possible to evaluate the composition and three-dimensional structure of a variety of materials, as well as provide information about the stresses under which a specimen was subjected. Polarized and cross-polarized light examinations can determine the relative vitrification levels of glazes, underglazes, and clay body, and mineralogical makeup. Vitrification is the transformation of a substance into glass. As clay material is fired in a kiln, it becomes more glass-like or vitrified. Glass is isotropic, meaning it has uniform properties in all directions. When viewed under cross-polarized light, glass appears black or disappears from view. Therefore, the more vitrified the material is, the darker it will appear under cross-polarized light. The more vitrified a clay or glaze is, the stronger or more impermeable it is. The image on the left is of the terracotta body showing the temper or grog and the pore structure. The sample was impregnated with blue epoxy, so all the voids and pores appear blue. The image on the right shows a clay slip over the clay body. The slip has a much finer texture than the clay body. Water absorption tests, specifically those in ASTM C67, contain procedures for determining the amount of water a sample can absorb, which can predict freeze-thaw durability. This test is fairly low-tech and requires soaking samples in water and calculating the weight gain. The samples are first soaked for 24 hours, weighed, and the percentage of water absorbed is calculated. The 24-hour soak generally simulates the amount of water that may be absorbed during a drenching rain. After weighing, the samples are returned to the vessel and the water is heated to boiling within 5 hours. Or excuse me, the water is heated to boiling for 5 hours. After 5 hours, the samples are weighed again and the percentage of water absorbed after the 5-hour boil is calculated. The 5-hour boil measures the maximum amount of water a sample can absorb. The saturation coefficient is then calculated as the ratio of the amount of water absorbed during the 5-hour boil versus the 24-hour soak. And this value is a predictor of freeze-thaw resistance. So here are the calculations, how you get the 24-hour absorption percentage, the 5-hour boil, and the saturation coefficient. Ideally, the saturation coefficient should be low. The closer the coefficient is to 1, the less resistant the material is to freeze-thaw damage. You want the masonry to absorb much more water during the 5-hour boil than the 24-hour soak. That means the masonry does not reach saturation quickly. In theory, if the masonry reaches saturation quickly, freeze-thaw damage is more likely to occur as all the pores are filled and there is no space for the ice to expand. If the masonry reaches saturation more slowly, there's empty pore space and room for expanding ice crystals. To revisit the Brooklyn Post Office testing, you can see in this chart that the 1933 terracotta had a higher saturation coefficient than the 1992 terracotta. So the absorption results mirror the freeze-thaw results. Freeze-thaw resistance tests confirmed the prediction of the saturation coefficient. Another way to measure water absorption is to use the Rylum test method 2.4. Rylum is an acronym that stands for this lovely French phrase right here, and I'll let you read it because my high school French is very rusty. This test measures the rate of water absorption through the surface. It can be performed on-site or in a laboratory. There are 2 types of pipe-like apparatus, one designed for horizontal surfaces and one designed for vertical. The flat circular end of the apparatus is affixed to the masonry surface using putty. The vertical tube of the pipe is graduated from 0 to 5 milliliters. Water is added through the open upper end up to the 0 gradation mark. The quantity of water absorbed over a known amount of time is then read from the graduated tube. The period of time appropriate for the test depends on the porosity of the material. I find that minute intervals for up to 20 minutes to be most effective. The results of the test are then presented in the form of a graph with the volume of water absorbed plotted as a function of time in minutes. Rylum tests were performed on these recently installed terracotta dormers. They were relatively new, but starting to exhibit shallow glaze balls, as you can see in the little red circles. So Rylum tests were conducted on the glazed surfaces, on the small cracks in the glaze, on the exposed body, and on the mortar joints to try to determine how water could be entering the terracotta. It was ultimately determined that the terracotta glaze was not absorbing any water, which is not surprising as glazes are relatively impermeable. The hairline cracks in the glaze were not absorbing water either. However, the mortar joints were absorbing a considerable amount of water. And if you look at our little graph here, down here, that's the water absorption after 5 minutes of the terracotta, and here's the mortar. Upon closer inspection, several mortar joints were desponded from the adjacent terracotta. These open joints allowed water to get absorbed into the unglazed bearing surfaces of the terracotta and cause the glazes to spall. The final test I'll describe is the compression test. As usual, good old ASTM C67 outlines the compression test method. So samples are first capped to create perfectly smooth and even bearing surfaces. And the samples are loaded into the machine, and the pressure is applied in a uniform rate until failure occurs. The compressive strength is then calculated as the load divided by the average area of the loading surfaces. Compression tests were used to evaluate the terracotta at Dickinson High School. The terracotta was severely deteriorated with cracks and spalls, and there was evidence of previous repairs which had failed and several replacement units. The compressive strength of 5 terracotta samples from the building were compared against ASTM 126, the standard specification for ceramic glazed structural clay facing tile, facing brick, and solid masonry units. The terracotta measured half the compressive strength as specified by ASTM. It was unclear whether the units were originally weak or deteriorated over time in service, but regardless, much of the terracotta was replaced as a result. So now that we've completed the testing and determined that the terracotta can be repaired, what repairs can we do? So I'm going to discuss a few common treatments and techniques that are performed to repair terracotta. Depending on the condition of the terracotta, its backup, and the anchoring system, these repairs can either be performed in situ or the terracotta can be removed, repaired off-site, and reinstalled. The treatments covered in this presentation include patching, glaze repair, grout injection, pinning, cleaning, and replacement. And as always, repairs must address the cause of distress rather than just treating the manifestation of the cause. These repairs should be performed once the causes of the terracotta deterioration have been addressed. Patching is probably the most common repair technique. Patching is performed to fill areas of loss in the terracotta. The patching material is typically a cementitious binder mixed with aggregate and pigments. There are several companies that manufacture materials designed to patch terracotta. All of them can custom match the color of the patching mix to the color of the clay body. Each manufacturer has specific mixing and application methods. Hands-on training sessions are offered by various companies, and some require certification, proving that you have been trained to use their materials. Before patching, the substrate must be clean and sound, free of all contaminants, coatings, previous repairs, efflorescence, and unsound material. The edges of the repair must have squared reveals to prevent feathered edges of the patch material, as patches with feathered edges would fail. If possible, a dovetail or undercut at the edges is ideal to create a mechanical key for the patch material. So here we've got some prepped surfaces here. The substrate is then moistened with water, and a slurry coat of the patching mix is applied, making sure all of the surfaces of the substrate are covered. This ensures the proper bond of the patch to the substrate and prevents the substrate from absorbing too much water out of the wet patching mix. The patching mortar is then applied to the slurry coat while wet. Deep patches may be applied in lifts to prevent slumping. Typically, the patch is then overbuilt and shaved or finished to match the adjacent contours of the terracotta once the patch becomes thumbprint hard. It must be remembered, however, that terracotta is a hollow clay block. Sometimes losses may be the entire depth of the face, resulting in a hole into the empty terracotta cells. It may be necessary to install a backing material to those voids prior to patching in order to support the patch. Excuse me. Some companies manufacture a patching material for filling shallow losses. This material is finer grained than the patching material for deeper losses and can be carved and sanded to produce a smooth finish. The substrate must still be clean of soiling, coatings, efflorescence, and unsound material, but the edges of the repair do not need to be squared off. So you can see in this picture, here's the little spall, and over here, and this is where the areas have been patched. Improper surface preparation and mixing can cause patches to fail. Too much water in the mix can create shrinkage cracks. Not enough water can cause the patch to crumble. Failure to clean the substrate, remove efflorescence and unsound material, pre-wet the substrate, or apply the slurry coat can cause the patch to disbond from the surface, which you can see here. This patch is disbonded from the parent terracotta. And even if the patch is sound, the surface must be properly finished to match the surrounding terracotta, Failure to do so will make the patches stand out, as you can see here. And you can see here in this example, while the patches are sound and the color is close to the original terracotta, the patches stand out because the texture doesn't match. Exposed terracotta body from failed glazes and repair patches must be coated. If not, water can be absorbed into the clay body and cause additional deterioration. While it's impossible to reglaze and fire the old terracotta unit, coatings are available to simulate the appearance and performance of the original glaze. These coatings are produced by several manufacturers and are typically urethane, acrylic, or mineral coatings. They come in an infinite number of colors and matte, semi-gloss, and glossy sheens. Typically, a clean sample of terracotta is sent to the manufacturer to produce a custom match for color, texture, and sheen. Like the patching material, replication glazes must be applied to clean, dry substrates free of contaminants, soiling, efflorescence, or unsound material. Patches must be dried or cured depending on the manufacturer's instructions and free of latents. So in these images here, you can see a contractor performing a glaze replication mock-up on the terracotta at the Brooklyn post office. As the terracotta was designed to resemble granite, the glaze had a mottled and speckled appearance to simulate the minerals in the granite. So the technician's applying the glaze in several stages. And the top left image shows the raw patch. The second image shows the patch has been covered with a light pink base coat, and the technician is beginning to add the black stipples. The bottom left image is the completed stippling, and in the bottom right image, the technician is applying a mottled white coating, a mottled white coating over top of the stippling. The glazes on these units are very glossy but visually varied. Again, a series of multiple colors were mixed and applied to mimic the appearance of the original glaze. The upper images show the bare patches before coating, and the bottom images are the patches after they've been coated. While replication glaze paints work really well for flat or complex glazes, they can sometimes stand out on uniform glossy glazes. It's very difficult, if not impossible, to match the translucent quality of some glazes with an opaque paint. So while the color of the replication glaze may match the original, the two materials will reflect light differently and the repair may stand out, as you can see in this bottom image right here. You can see the different colors. You know, like this one is a really good match, but it doesn't reflect light in the same way. It's also very important to remember when obtaining color matches that there are often several slight variations of the same color. Here, the contractor used only one color for the pale pinkish white terracotta glaze. While it was an appropriate match for some units, it clearly stood out against the darker ones. And you can see all of the little patches with the called out with the red arrows. So depending on their size, cracks in terracotta can be filled with an injectable grout. Typically, cracks between hairline and 1/8 of an inch wide can be grouted. Wider cracks can be patched. While the pictures on the screen are not technically terracotta, they're granite, the procedure for the grout injection is the same. The cracks are first cleaned of contaminants, soiling, debris, and loose material. And then injection ports are drilled down the center of the crack in a downward direction. The interior of the crack is then flushed with water immediately before injection. Failure to do so can prevent the grout from flowing into the crack. The surface of the crack is then sealed with a non-staining clay, leaving the injection ports open. The grout is then pumped into the crack through the injection ports. Once the grout is dried, the clay is removed and the surface of the crack and the injection holes are patched and painted to match the surrounding glaze. Injection grouting can be very tricky to do properly. First, as previously stated, terracotta is a hollow material. If you inject grout into cracks that extend through the entire terracotta face, you'll be pumping grout into the terracotta cell. If the crack is not cleaned thoroughly, debris can inhibit the flow of the grout through the crack and leave voids. If the crack is not pre-wet properly, the terracotta can absorb too much of the water out of the grout and inhibit flow. Therefore, grouting should only be performed by technicians who are very familiar with working with the material. Cracked and broken terracotta can theoretically be pinned. Broken pieces of terracotta can be pinned together, or loose or broken terracotta can be pinned back into the backup masonry wall. There are several types of pins available that work in different ways. Common pin types include helical ties, grouted sock anchors, and threaded rods. Helical ties and sock anchors can be used to pin loose or broken terracotta back to the substrate. For the helical ties, a small pilot hole is drilled through the terracotta into the backup masonry. The helical tie, which is slightly larger than the pilot hole, is then drilled into the hole and set below the face of the terracotta unit. The hole at the surface is then patched and coated. Sock anchors are also installed in terracotta and backup masonry through an oversized pre-drilled pilot hole. Then a special grout is pumped into the anchor, surrounded by the fabric sock. The grout fills the sock, which creates keys in the voids of the terracotta and backup masonry, thereby holding everything in place. Conditions have to be ideal for this to work properly, and very rarely are conditions ever ideal. The terracotta must be in sound condition, except for the break. Friable terracotta cannot be pinned as the material would be too weak to accept the pin. The backup material must also be in sound condition in order to support the terracotta being pinned into it. However, pinning can work as a temporary measure until terracotta can be removed, subsurface conditions corrected, and new terracotta installed. Cleaning is a treatment that will have the greatest visual effect on your terracotta restoration project. Often, owners want to see a pristinely cleaned facade to justify the money they've just spent on the restoration. While cleaning does not seem to be that technically difficult, it is the easiest way to permanently damage the terracotta. Glaze chemistry is varied and complicated. Cleaners that have worked without damage on one terracotta project may not be safe for use on the next terracotta project. Improper cleaning products can etch glazes and cause discoloration, as is shown in this image. See all the yellow staining from a potentially acidic cleaner. Therefore, a thorough cleaning test program should be implemented prior to full-scale cleaning. A variety of cleaning products should be tested, taking into account the soiling types and glaze characteristics. For polychrome terracotta, testing may be necessary for each color. Testing will also be required for different types of soiling. Testing locations should ideally be performed in out-of-the-way locations to minimize the visual impact of any adverse effects. When evaluating cleaning tests, it is always better to go with a cleaner that does not remove all of the soiling to avoid over-cleaning the terracotta. Also, historic buildings should retain a patina of age. They do not and should not look pristine or the way they did when they were newly constructed. The reasons for cleaning should be determined as part of the restoration program, and it may ultimately be decided not to clean the building. However, one of the common reasons for cleaning a terracotta facade is to have replacement units fit in. The glaze on a newly manufactured replacement units should match the color of the cleaned original glaze. And cleaning the old terracotta will prevent the restored facade from looking like a patchwork. This slide shows a mixture of original and new terracotta. The newly manufactured terracotta units do not stand out due to cleaning. So you can see here, these piers are a mixture of new and old terracotta. This is all new, and this is old. The final treatment discussed this evening will be replacement. Terracotta units that cannot be repaired should be replaced in kind with new terracotta to match the original. Lead time for new terracotta can take up to a year, so that should be factored into the construction schedule. But replacement in kind ensures physical compatibility with the original material. Alternate materials like GFRC, GFRP, cast stone, and cast hollow block may be considered. They offer the advantage of faster production times, particularly for new replacement pieces. However, they must be seriously evaluated. They require an understanding of the weathering characteristics, material compatibility, preferential deterioration in relation to the original terracotta, and new framing and installation methods. I'm not going to go through all the different replacement options in this presentation, but I'll quickly go through the steps required from specifying new replacement terracotta through to installation. And while I'm using replacement with terracotta as the example, this process will still generally be the same for any alternate replacement material. Typically, the terracotta manufacturer first visits the site to survey and measure the terracotta scheduled for replacement. Each unit is given a unique label, and often representative samples of each type of unit to be replaced are removed for the model and mold making. The manufacturer then produces shop drawings showing unit layout and anchoring. The image on the left shows the unit layout and unique labeling system for each unit. The image on the right is a setting drawing indicating the type of anchor to be used for each unit. Here, the anchors are given a letter designation. So you can see all the little C's and D's on this image here. Shop drawings for each unit are also produced. These drawings show the overall dimensions of the units, the cells, the web walls, the glazed and unglazed surfaces, placement of weep holes, and ornamental details. Glaze matching is a long process that requires several attempts to match the glaze, so it should be started as soon as possible. One of the biggest complications with matching historic glazes is that many of the materials used to create the glaze are either no longer available or have been banned for use, like lead and chromium. While it's obvious that each unique color will require a match, there's often a range within one color type. In the example on the left, there are at least 4 different shades of blue that needed to be matched. In the example on the right, there were 4 subtle shades of white that required matching. The images on the top show the original terracotta colors, and the images on the bottom show the replicated glazes. Failure to represent the range of colors will make the replacement units stand out from the original. Models and molds of the terracotta units then need to be made. Ideally, samples removed from the building are used to make the models, as shown in the upper left picture. The models are slightly larger than the original to account for clay shrinkage in the drying and firing processes. The models are then used to create plaster molds into which the raw clay will be pressed. When samples cannot be removed from the building, molds can be cast in situ as shown in the bottom images. However, new models and molds must be made from these site molds, which are larger than the existing, again to account for shrinkage. Often at the modeling stage, the architect, contractor, and conservator visit the fabricator to approve the models before production begins. At this time, any corrections to the forms can be made before fabrication. Once the models are approved and the forms made, the forms are filled with clay. When they have sufficiently dried, the molds are removed and the pieces are finished by hand. In the finishing process, deep undercuts of highly figured pieces are carved. Any abnormalities from the models are corrected. The surface textures are applied, and each unique number is stamped into the clay. The units are then put in the dryers, glazed, and fired. Oversized units are factory cut to the proper dimensions prior to leaving the factory. And finally, after several months, your new terracotta arrives at the job site. Using the shop drawings and the unit numbers as a guide, the new terracotta is installed in their respective locations. The new terracotta units must be pre-wet prior to installation. The terracotta is extremely dry from the manufacturing process and can absorb too much water from the mortar, causing failure of the mortar joints, not the unit. Terracotta units must not be filled and are typically hung and supported by stainless steel anchors, you can see them right here, that are embedded or attached to the backup wall. Anchor holes are modeled into the pieces during fabrication based on the shop drawings. Fabricators do not recommend filling their terracotta. Filling units can cause water to get trapped within the fill, expand when frozen, and crack the terracotta. The images on the right show a new terracotta bollard that was filled with grout for structural purposes. The bollard cracked within weeks of being installed. So new terracotta bollards had to be fabricated and installed. So I hope I was able to give you some basic information on what should be considered when approaching a terracotta restoration project. No two projects are alike. There are a myriad of variations to account for, including the terracotta itself, installation techniques, deterioration mechanisms, and repair options. Therefore, these projects require expertise, attention to detail, and a little imagination. Thank you.
Helen,
Yes.
that was just terrific. Your
Thank you.
exhaustive knowledge, it's like as I mentioned at the beginning of the talk, it is just so impressive. And it's almost like, is there anything we could ask you about terracotta that you wouldn't know? And I think the answer would be no, because really anyway, thank you. It was a really wonderful lecture. And we're just so delighted that you were able to share your expertise with us tonight. Victoria, would you like to say anything? This is Victoria Dangle, our Executive Director.
Yes, Helen, well, thank you. And that was your expansive knowledge. But I have to ask you, because you're consumed with the subject in the best of ways, what inspired you to specialize in this particular area? Where did you grow? I'm curious also where you grew up.
I am a born and bred New Yorker. I was born in the Bronx, raised in the Bronx, live in the Bronx.
Did you see a lot of terracotta I'm also a native New Yorker. What part of the Bronx? So curious.
Oh, the Northeast Bronx. Okay. I'm all the way at the top.
Yep.
Well, you know, growing up in the Bronx, you know, you're not really, you know, in the 80s and the 90s, you know, historic preservation was not a thing that was focused on, was taught, or anything like that. But then when I went to college, I happened to go to Mary Washington College, which is now the University of Mary Washington in Fredericksburg, Virginia. And they have an undergraduate degree in preservation. And I took some classes and it covered a bunch of stuff that I loved, architecture, art, science, and then it stuck. And so then, you know, I came back home and then went to grad school at Columbia, and then having, you know, that background, you know, now you walk through the city and you see it, right? You recognize it, right? It's not just background anymore. And so, you know, working for JBC, I had the opportunity to work on quite a few terracotta projects. It's not, you know, it's become, it's not my only interest, but it has become, you know,
Your
one of them.
specialty, yes. And growing up around, I find buildings, oh my goodness, you know, there's such a comfort to even, you know, I stopped, I'm always walking along. My sister is always telling me, you seem like a tourist yourself, but I'm fascinated by terracotta, the facades. It's just an old New York. So thank you what you do to preserve that. And I just want, another question comes to mind, the 15,000 terracotta units. We had like 4 on this building with a major restoration. So 15,000. And how long did that take to come back manufacturer-wise?
I'm trying to remember. I can't exactly remember. But you know, when you've got a large scale project, obviously you schedule, you know, with the contractor and the manufacturer where you're working, right? So you work on facades, areas, you know, elevations at a time. So obviously 15,000 units don't show up at once. And then there is a production flow that happens. So again, you know, it's something that needs to be factored and considered when you're doing your construction schedule. Like, what's your phasing? How are you, you know, if you've got a large project, how are you scheduling things to come back, basically? What are you working on first?
Right.
Yes. And Helen, I'm going to turn this over to the audience because so many things ran through my mind as I was listening to you. Now with landmarks preservation, now where you can no longer you have to fabricate terracotta itself. Has that what's been the impact in all of these aging buildings? There must be a lot of there's a lot of terracotta in New York. So
there is.
Yeah.
There is. And you know, manufacturers are busy.
Yes.
Oh, and there's only a couple, right?
Yes, in the United States. Yes, there are 2.
All this fabrication. So
yeah, it's a challenge. It's a challenge.
Yes.
Yes. Well, no wonder there's a year wait, right? That explains that. So we do have some questions from the audience. This is from Mary Derrick.
Mary.
First of all, she thanks you, and that was illuminating. Do you think the difference in glazing color in white terracotta is just weathering, or is it design intent? Okay. Okay. Well,
no, I think I don't know if it's necessarily design intent, right? I think that there becomes like a natural variation that occurs during the firing process, right? So depending on temperatures and placement in the kiln, and can cause the same glaze to just have a slight variation in color thickness. So I think it's just a natural byproduct of the manufacturing. But some glazes I think do change a little bit. Not too much, because they are glass, and once they're fired, sort of become inert. But they do get stained, you know.
Right.
You know, we've seen staining happen a lot with the faience in subway stations, right? Because there's all the brake dust and the steel that stains it. So the answer is yes.
Right, and I'm going to ask, I'm going to ask sort of
It's not
thank
complicated.
you. A sort of similar question on that topic. This is from Susan Tinnick, who's part of the Columbia faculty. How frequently do you think aging is an important factor?
Is there more to the question?
No, I'm afraid that was it.
Aging is a factor for what? Can you explain it a little bit more, Susan?
Well, I tell you what, we'll ask Susan if she would expand her question, and
I saw there was a pop-up that came about LPC. It says you do
Yes.
not always have to replace terracotta in kind in LPC buildings. So
right. Well, yes, there is, and as the audience will see, you addressing the subject that came up before. You do not always have to replace terracotta in kind at LPC designated buildings. So just to be aware of that. And then indeed, there is a link to the LPC permit guidebook.
Is that new, Helen? Because I mean, it used to be where you could fabricate, a fiberglass replacement, but then, and I have one of our members does quite a bit of work with the Schubert organization and lots of landmark buildings there. He experienced the same thing. We were told it can only be terracotta itself. So, interesting. I have to read more about that. Thank you.
Right. Well, let me address some of the other questions.
Mhm.
When applying glaze to a terracotta patch repair, what is the recommended treatment for the edge of the patch at the transition of the original glaze? And that's from Ian Zerwitsky.
Well, I know that some of the manufacturers have a primer that you can use, that you can put on the existing glaze, so that if you do a slight overlap, it will attach. What happens is, if you've got a very glossy glaze and you apply some of these replication coatings to a glossy glaze, they won't stick. So there are primers that will help that adhesion. I typically don't try to do much of an overlap because it can, well, you end up seeing it sometimes, and sometimes it can be a point of failure, but a little overlap, maybe depending on the size of the piece, an eighth of an inch, a quarter of an inch is usually enough. But you have to prime it.
Right. This is another question from this is from an anonymous attendee, and it's actually a very pertinent question. How long can terracotta last on a building like Brooklyn Post Office? And indeed, let me ask my own question. How long can you normally expect, replace terracotta to last? I understand weather conditions may have an impact, but
yeah, forever.
Forever.
Really?
Okay. Well, that's a
um,
great answer.
Because I mean, just like, stone or brick or masonry, it's what deteriorates it is so subjective and specific to the site, specific to the condition. In an ideal world where water isn't getting in through open joints, and you've got a perfectly sealed building, and you've got stainless steel anchors, you're not dealing with corroded ferrous anchors, the terracotta can last forever. There's ancient terracotta, there's Roman terracotta that's still
Right.
around.
Okay, well, that's fantastic to know. And I'm so glad that terracotta that's just been replaced in our building will be around for a very long time. That's great to hear.
Yeah, I mean, what's good? I mean, mortar joints may fail, which then may cause the terracotta to fail, but the terracotta itself, you know, it's not like terracotta breaks down per se, right?
Right. There's another question from Stephen Summers. Are the terracotta medallions in the Bleeker Street station original or restored? And he also asked, could you discuss briefly the NYC subway terracotta generally, many of which are quite beautiful?
So the big plaques that say Bleeker Street are original. They are cleaned and slightly patched in places, but all of the pieces are original. The terracotta faience on the top of the wall in the extension, there are extensions on the north and southbound platform that are completely new. So that's all new terracotta. In the original sections, it's a mixture of repaired and new terracotta. So I dare you to go find which are which.
Okay.
I personally repaired that terracotta.
And I just want, Joan Berkowitz has weighed in.
Hey, Joan.
Yes, and about because Joan, hello, Joan, consulted on this building with Howard Zimmerman. So Victoria, your building is an individual landmark and the units are below the 6th floor. Those two factors meant that you needed to replace in kind. So that settles that.
That's the law.
Yeah. Thank you, Joan, for that clarification.
Hey.
We'll just take, we have a few more questions, if that's okay with you, Helen?
Keep them coming.
Right.
Keep them coming.
This is from Arthur Platt. Is terracotta prevalent as a modern rain screen cladding? I know Renzo Piano and others have specified it. And then he asks, how does it perform in freeze thaw or water absorption versus when adhered pinned directly back to backup material?
I know that Boston Valley Terracotta is trying to do a rain screen, has a line of rain screen products. I am actually not familiar with its performance. I have not been asked to look at any of those buildings. So I fortunately cannot answer that question. I don't know about its longevity.
Okay.
In 50 years, I'm gonna.
Okay.
Right, when it all becomes historic,
No.
it's gonna be.
This is from Jane Schriebman. What makes terracotta different from brick?
They are very similar, right? So they are both formed and fired clay. I guess what makes terracotta different is that it's hollow and glazed, and it's trying to be stone for the most part, architectural terracotta, and it's got a glaze on it. Where brick is, although there is glazed brick, is typically not glazed.
Right.
But the ASTM C67 test that I referenced, or standard that I referenced quite a bit during my presentation, the tests in there are for both brick and terracotta because of their similarities.
Okay, thank you. Okay, I'm going to take 2 more questions. This is from Anthony Fioro. How long are molds stored for given their size?
Say that again?
How long are the molds stored for given their size? I suppose he's thinking about very large molds. I'm
Oh,
guessing.
molds.
Yes.
I don't know. That depends on the manufacturer. It also depends on whether the client or the owner wants them back. Sometimes it's written in the specifications that the molds be returned to the owner. The molds are typically made out of plaster. So I think, you know, after a few uses, they do start to break down. They, you know, they get clay stuck in them. So I think several molds are made during a process, but then after the project, I don't know if they're kept. Was that the question, or?
Yes, I think so. Yeah, well, I think you gave a very comprehensive answer, so that's great. And
I hope I'm not rambling.
No, okay, not at all. This is going to be our final question. This is from Matt Gaffrey. Is there any strategy or method for replacing defective terracotta units that may be located surrounding other units that are not defective without having to remove the surrounding units?
Yes. It's hard, again, to give like a one size fits all answer. Sometimes what can be done is, if the defective unit is completely destroyed, you know, from deterioration, you can, you know, cut the joints on either side and then completely destroy the unit that you want to remove, while leaving the surrounding in place. But then it depends on how they're anchored, how they're installed. But it's done quite often, because as you said, Victoria, you just had a few units on your building that needed to be replaced. So, but typically, if you've just got one, you destroy that one to get it out.
Right.
And then you have to design special anchors to put it back in if you can't access the back. And that's where engineers come in.
Okay.
Because a lot of terracotta repairs require engineering interventions for hanging, for supporting,
Right.
that kind of thing. Want to make sure that they're on there good.
Absolutely. If they're going to last forever, yes, absolutely. So Helen, I just want to express our huge appreciation again, and I'm going to read a comment from Constant Melrose, which I think sort of summarizes it very well. Amazing, thank you. Living in New York is eye candy for those of us who've fallen in love with buildings. Thank you for bringing this to life, and I really think you did that so effectively.
Thank you.
And as I said, your expertise and vast knowledge, you have literally brought terracotta to life. And I'm so glad to know that our terracotta and everyone else's terracotta, if treated properly, will be around forever. Yes. So Victoria, would you like to say something in conclusion?
Helen, I just want to say you're a wonderful teacher.
Oh, thank you.
You took a lot of information and you distilled it in a short, you know, in a very brief period of time. We all know a lot more, and that is not, and it's not an easy task. And we're really looking forward to meeting you in person. We can't wait till you visit at the General Society of Mechanics and Tradesmen. And thank you for making this so enjoyable. And I love to see that you love what you do, and you could see that you have true enjoyment doing it. So thank you. And thank you for taking care of this great city, and to the firm that you know, Jablonski. If our viewers go, if our guests go to the website, what a first of all, it's very well done. All of the projects, you know, the scope of work, the photos, that, you know, if people want to continue to learn about these great projects that your firm does and that you're engaged in. So thank you so much.
Oh, my
for
pleasure.
your generosity tonight. Thank you.
Thank you.
Absolutely. Here. I just, so before finally thanking Helen, I just want to mention two of our upcoming events. On Thursday, November 4th, we'll have a Book Lover's Guide to New York with author Cleo Latan. And on November, we will have a lecture that was postponed from October, and that is Iconic Design That Transformed Times Square. Tickets both in the heart of of Times Square with Nick Leahy of Perkins Eastman, and that will be a hybrid lecture. So again, Helen, our great gratitude. I also want to thank Connie for suggesting this and making this happen, and indeed Helen's colleague Mary, who spoke here in July. Again, thanks to you, the audience. Oh, and I also want to thank Angelo, who's been behind the scenes tonight. So thank you very much for that, Angelo, and indeed to the Conservancy, New York Landmarks Conservancy, and Archtober. So thank you. Good night. We look forward to seeing you again.